you like to spend some time in a habitat on Mars and become part of the greatest adventure in human history, to boldly go where no one has gone before, to live and thrive where no human could even survive before, and maybe encounter new life forms that no human ever has encountered before? But when will the day come? And how realistic is your chance that you will be among the very few chosen ones to set foot on Martian soil in 15 or maybe 20 years? Well, with our new project, you can experience what it is like to live in a Mars habitat. Not in the near future and not in the distant future, but right now and here, in the heart of Europe. So, let's have a look. An inflatable Earth house. This is not only the future of living on Mars, but a new way how humans can live in harmony with nature here on Earth. The building structure consists of a thin double-layered membrane, compressed air and natural soil. For over 18 years, we've been designing, developing and producing inflatable buildings. This specific project began 3 years ago when we developed a lunar habitat for the European Space Agency within the OSI program. That concept was based on ultralight inflatable modules, easy to transport inside the spacecraft and quick to deploy on the moon's surface. A protective layer of loose lunar regolith shields the habitat from cosmic radiation, meteorite impacts and extreme cold. A novel, patented mirror system directs sunlight into integrated greenhouses, enabling the autonomous production of food and oxygen. Through this work, we came to a crucial realization that this construction principle also makes sense here on Earth. This insight led to the idea of a cost-efficient, prefabricated, modular inflatable Earth house, a building concept that operates with a minimum of resources and energy. Now we have completed this prototype, once again with the support of funding from the European Space Agency.
Hallo Stefan. Hallo Thomas. Okay, kannst du. Ja, das ist.
Are you
Ist
warm
euch warm
enough?
genug, ja? Alles?
Ja,
Good.
wunderbar.
Currently, we do not use any active heating. The building is insulated with 20 centimeters of heat insulation and embedded into the ground. The outside temperature is currently around 0 degrees Celsius, but the surrounding soil still maintains a temperature of about 10 to 12 degrees. The deeper the soil layer, the more stable the temperature remains throughout the year. In Central Europe, outdoor temperatures can range from -20 to +40 degrees Celsius. At a depth of 3 meters, however, the ground temperature fluctuates only slightly around +10 degrees. In addition, the soil reacts to seasonal temperature changes with time delay. It warms up later than the air and cools down later as well. As a result, the annual temperature peak shifts from July to October, and the lowest point shifts from January to April, a time when outdoor air temperatures are already rising again and higher solar gains are available through the windows. For an Earth-integrated house, heat transmission is therefore reduced by at least 50% compared to an above-ground building with the same level of insulation. The soil itself also provides an additional insulating effect. In summer, the situation is reversed. Keeping the building cool becomes significantly easier. The ventilation system plays an important role here. Fresh air is drawn through 2 pipes, each 25 meters long, which run through the surrounding soil. As the air passes through these pipes, it is cooled to the temperature of the ground and then cools the interior as it enters the living space. Warm exhaust air leaves the building through a third channel, transferring heat back into the soil. In winter, supply air and exhaust air additionally exchange heat via a heat recovery unit. When the building geometry, insulation and ventilation system are designed correctly, the building requires no energy for heating or cooling. Energy efficiency is not only important during operation. The energy needed to produce building materials is a key factor in the overall energy balance of any building. Producing 1 cubic meter of reinforced concrete wall requires 1,400 kilowatt hours of energy. Today, around 37% of the global CO2 emissions are attributable to the construction industry. In a Inflatable Earth House, most of the building mass consists of the surrounding natural soil itself. For every 100 square meters of living space, we save 170,000 kilowatt hours of primary energy compared to a conventional building of the same size. With this amount of energy, you can drive an electric car over 1 million kilometers. The building also integrates discreetly into the landscape. At the moment, in November 2025, what we see is a bare mound of earth and a small plastic dome emerging from the ground. By next spring, this will be covered with grass and flowers. In addition, we will spray a layer of polyurethane insulation foam onto the exterior of the roof. This will form a highly stable rigid foam shell capable of supporting up to 80 centimeters of soil. As a result, the entire building disappears beneath a green surface and it remains structurally stable even without internal air pressure. This also makes it possible to integrate unpressurized rooms into the building with doors that can open directly onto the garden.
Jetzt würde das wie viel kosten, wenn das in Produktion?
According to our calculations and also our experiences with the prototype, I can say in serial production, construction costs for a move-in ready residential building are expected to range between 2,100 and 2,400 euros per square meter of living space, including 20% of value-added tax. In the Inflatable house, the modular components are prefabricated in series. Because both transport weight and transport volume are minimal, the most cost-efficient production locations can be selected globally, independent of where the building is ultimately installed. Many of the trades required for a conventional building are no longer necessary. There is no need for a complex heating system such as a heat pump. Along the edges for the triangular cushion elements, Velcro fastening strips are integrated. These allow electrical wiring to be routed quickly and invisibly, without any cutting in the walls and without the need for empty conduit systems. The same Velcro strips can also be used to attach modular shelving and other furniture elements, such as textile wardrobes. Each triangular cushion is additionally equipped with a welded eyelet, allowing artworks or furniture to be suspended directly from the structure. The floor construction includes, among other layers, a 20 cm deep gravel bed. This layer accommodates not only electrical cables, but also larger pipes for water supply and ventilation. For sanitary areas in particular, the design foresees dividing a larger room module with a straight gypsum plasterboard wall. This flat surface allows standard, commercially available rectangular built-in furniture and appliances to be installed for kitchens and bathrooms. The simplest and smallest module is a sphere flattened at the bottom. Its double-layered outer shell is in turn divided into a grid consisting of triangular soft inflated cushions. The surface of these triangular cushions is made of comfortable textile material. They also can be transparent and serve as windows. By intersecting 2, 3, 4 or 6 spherical modules along the triangular grid, we create further larger types of room modules. These are arranged together to form complete buildings in a variety of different possible floor plan types. This is the prototype in its first stage of development, and with this we have proven that our concept works. One not so small step for a man, one giant leap for mankind. And many more steps still lie ahead. Over the next 2 years we plan to add a full kitchen and bathroom module and a large living room. We invite investors and competent partners for the next phase. Not only for money, but also for sharing common dreams and goals. So, are you ready to take the giant leap? Let's reach for the stars, or at least for Mars.